Hello, Mr. Betts here. I want to take a look at an example that uses that special case of the first derivative test. So remember, the first derivative test tells us that if a function's derivative changes signs at a point where that function is continuous, then we're going to end up with a relative minimum or a relative maximum at that point. So for example, if the first derivative changes from positive to negative, then the function itself changes from increasing to decreasing, and at that point we get a relative maximum. Now, the first derivative test generally only gives us relative extrema because it tells us what's happening around a single point. And so we don't know what's going on elsewhere, and a function could do something like this, and we could have other maxima or higher values of the function away from that point. There is a special case, though, where we can use that first derivative test to find absolute extrema. So let's get started here, and we're just going to start the first derivative test like we normally would here. So we will start it by taking the first derivative. We have to use the product rule here. So derivative of the first times the second plus the first times the derivative of the second. And with the first derivative test, we want to find critical values. That derivative is never going to be undefined, but it will be equal to 0. So it's going to equal 0. We get critical values at x equals -1. And that's actually the only critical value because e to the x is never going to equal 0. So the next thing we're going to do with the first derivative test is we're going to organize our information about the derivative using a sign chart. So I'm going to make a sign chart for the first derivative. Remember to label that sign chart. And we're going to put critical values on there. So to the left of -1, if we plug in some big negative number into the derivative, I'm going to plug it into this version of the derivative right here. E to the x is always positive, and 1 plus a big negative number is going to be negative. So this is going to be negative on this region. And then if we plug in any number bigger than -1, so any positive number, 0, anything like that, we're going to get a positive times a positive, which is a positive. So based on the first derivative test, we can say f has a, so since the derivative changes from negative to positive, that means the function changes from decreasing to increasing, and that's going to give us a minimum. So I'm going to label it right now as just a minimum at x equals -1. And then let's be a little bit more specific here. It is a relative minimum. That's true because this is going to be the lowest value in the neighborhood around -1. But also, since the function itself is decreasing for all values of x to the left of -1, and it's increasing for all values of x to the right of -1, we have a function here that goes from always decreasing to always increasing. Now, I don't know exactly what this function looks like, but I do know that we're not going to see anything on the function. So here's x equals -1. We're not going to see anything that does this and ends up below because we would have another critical value here. We're not going to see anything that does something like this because this function is a continuous function. So I know that going to the right, all the values have to be greater than the value at -1 because the function's always increasing to the right. Likewise, going to the left, all the values are going to be above the value of the function at -1 because the function itself is always decreasing. So it's increasing going to the left, but remember we're going left to right, so it's a decreasing function. So based on the fact that it only has one critical value, we can identify this as an absolute extreme. Okay, so this is an absolute minimum. And then it does say justify your answer. So we want to justify our answer using calculus. So we're going to say because. So the reason that this is an absolute minimum is because f is continuous. And we can verify f is continuous by noting that the derivative is always defined. So since the function's always differentiable, it's also always continuous. So f is a continuous function and has a single critical value at x equals -1, which is a minimum by the first derivative test. And really, I should justify that by saying that the derivative changes signs kind of a lengthy description, but the idea here is that since the derivative only changes signs at one point, then we know that the function itself is always decreasing to the left, always increasing to the right, and so we have an absolute minimum at this point.